All right, it's time to start. Good morning, everybody. Today we will talk about protein thermodynamics. So we will continue from chapter 12 that you've done 2 weeks ago with Anton. So first, a quick hey. Yes. So first, a quick recap of chapter 12. So just to see a little bit what you remember. So if we have a free energy diagram, so we see the free energy on one side and the reaction coordinate on the other side. And you have a protein that's is either in state 1 or state 2. Which one of the two is more stable?
State 1.
1, yes, because it has a lower free energy. And if a protein is in either state 1 or state 2, does it stay there or can it switch? It switches. Yes, so protein is never just stuck in one state. It's always dynamic. It's always dynamic. Yes. So the most stable state has the lower free energy. So if you just look at all multiple proteins in the system, which one are you more likely to find? Which state are you more likely to find the protein in? Yes. Yes. So the most stable one. That makes sense. So which state is most stable depends on the system conditions. So, for example, if you would change the temperature or the pH, then this free energy diagram could look very different. Yeah, so under physiological conditions, what we usually refer to as the native state is the most stable one, so that's quite often the functional state of the protein. So protein unfolding and unfolding is stochastic, so when a protein is either state 1 or state 2, it has a certain probability to switch, and sometimes it will, sometimes it will not. Yes, and this one we already touched upon, it's dynamic. So in this lecture, we will get a bit more of a formal introduction to free energies. So there's two kind of main concepts that you should get at the end of the lecture. And the first one is that the free energy difference between two states depends on the enthalpy, so that's the energy in the system, and your entropy, which says something about the flexibility of the system. And the second one is that the probability of the free energy of a state is proportional to the probability to find a protein in that state. And before we, so this is, we will go into in more depth in the rest of the lecture, but before we do that, we will go more into this dynamic equilibrium. So for example, if we take marbles in a box, we have these red marbles and blue marbles, and we start with the sorted state. Now, if we shake the box, you get a mixed. They become mixed. Now, if we take the mixed state and we shake it even more, they will stay mixed. They will not go back to the original separated states. So now we can say, if you if you think about this one. Yeah, so if you look at the marbles that are in one side of the box or the other one, the number of marbles that changes at some point will not switch anymore. So the number of marbles going from one half of the box to the other will equal the number going back, and that's when we say it's dynamic equilibrium. So the marbles still move, but they don't. The total number in each side doesn't change. We can do something similar with proteins. So if we have, if we look at our free energy diagram, so we have an energy barrier, so the protein can switch from state 1 to state 2, and from state 2 to state 1. But there's this energy barrier that prevents it from doing so. And basically, the higher the barrier, the lower the probability that your protein will change. So in this case, barrier 1 is higher than barrier 2, so the probability that a protein goes from state 1 to state 2 is lower than the probability that your protein goes from state 2 to state 1. So in equilibrium, so the probabilities are different, but in equilibrium, so the number of proteins going from state 1 to state 2 is the same as the number of proteins that goes back. So if we say that we start with a situation where there's more proteins in state 2, because the probability of going from state 2 to state 1 is also higher than the probability of going back, we will have more proteins going from state 2 to state 1. And thus we are not in equilibrium yet. Now, if we have some value where there's more proteins in state 1 and state 2, because the probability of going from state 2 to state 1 is higher than the probability of going from 1 to 2, if the number of proteins in state 1 is actually higher, the total number that switches can be equal, and then we are in equilibrium. So if you think about this dynamic equilibrium, what does this mean for example, if we do experiments where we take where we study properties of these proteins in their native state? Anybody have an idea?
The single protein will maybe not stay in the same state, but overall all the proteins have a certain fraction will always be in the native state.
Yeah, so actually if you're studying proteins in their native state, there's always a couple that are actually not in their native state. Now, usually when we do experiments, this energy barrier is so high that the switches don't occur very frequently. And usually in these stable states, the vast majority is actually in the lowest free energy state. So that's actually when we do these experiments, we kind of assume that all the proteins, because almost all the proteins are in their native state. So if we think about our marbles again. Why does this not happen? In principle, what prevents the marbles from going back? Because there's nothing that says the marbles that they have to stay mixed. Now, this has something to do with kind of the probability to be in a certain state and the number of ways you can be in a state. So if you think about the separated situation, there's only one way in which you can separate, put all the red marbles on the left and all the red marbles on the right, all the blue marbles on the right. If you mix it, you can do this in many, many ways. So actually physically there's now nothing preventing the marbles from being in a shorted state, but just because there's so many more possibilities for the marbles to be mixed, they just the probability that you will find the marbles in a sorted state is so low that you actually in practice don't see it. We've also talked with Anton a while ago about Leventhal's paradox. So if you think about proteins, to visit all the possible conformations of the proteins, you would actually need more time than the life of the universe. So that's why you actually, so the very, very low probable states you will not visit just because there's not enough time to actually go there. Yes, so the probability that they are mixed is much higher just because there's a larger number of mixed states. And this relates to the entropy, so there we go to our first physical concept of our free energy. So the entropy here indicates is related to the flexibility of the system or the number of configurations a certain state can be in. So in this case, there's a higher entropy than for the sorted state. So if we do it on proteins, you've already seen this picture before as well. So if we take a 2D lattice model with hydrophobic, that's the yellow ones, and blue is polar amino acids, and it's 6 residue peptides, then these are all the conformations that this protein can be in. Now you see that if it's unfolded, there's many, many states, and if you go to the native state, the folded state, there's only one way to be in this state. So there's a very low entropy for the folded state and a very high entropy for the unfolded state. Now if we go a bit step further to actual real proteins, so if we take a look at this NMR structure of a protein, then in a continuous model, of course, you cannot count the number of states because that's infinite, but you can say something about the flexibility of certain structural regions. So here we have, if you look at the secondary structures, secondary structure elements in this NMR structure, you see that that these secondary structure elements for all the different conformations that have been measured are very, very similar. There's a large overlap, but if you look, for example, here at the C-terminal, there's a lot of flexibility. So actually, so here you can see a region with high entropy in your protein. Then, so if this unfolded state is much more likely, why do we find the protein very often in its folded state? And the answer of that, of course, interactions. So that's where the second concept comes in, the enthalpy of the system. And so if there's a favorable interaction here between the hydrophobics and the polar residues, then in certain conditions you will find this folded state because the energy is so favorable that even though the entropy is not so favorable, it's still the most stable state. And then if you would think about our marbles, so if the red marbles attract each other and the blue marbles attract each other, then so it's more likely to find the box in the state. So the entropy is going to be internal energy of the system, so you can think about potential energy, but interaction energies, so von der Waals interactions, hydrogen bonding, kinetic energy, those all contribute to the energy in the system. And for example, you don't have to remember the formula. If you look at the Lennard-Jones potential, so that's so here you have the distance between two atoms and the energy, interaction energy between these two atoms. So if you have the two atoms, if they come, if there's a very large distance, there's no energy between them because they can't feel each other. Then if they come closer, they are attracted to each other. But at some point, if you push them together too much, they will start to repel each other. And then you see here there's a kind of energy minimum where the atoms most likely want to be. So that's an example of what an energy, what these energies can look like. So the free energy, come back to our formula, so that's the enthalpy, so the energy of the system, minus the temperature times the entropy. And then we know the lowest free energy state is the most stable state of the system. So that's a trade-off between having a low energy and a high entropy. Because typically we think of the unfolded state that has a very high energy because, for example, the hydrophobic residues are exposed to the solvent, so they interact with water and they don't like that, of course, so then you get a high energy. But the conformational freedom of an unfolded protein is higher than for a folded protein, so it also has a high entropy. And then if you look at the reverse, so if you have very many favorable interactions, then you have a low energy, but then you also don't have a lot of configurational freedom, so then your entropy also goes down. So so low entropy, favorable interactions lowers the free energy, and the high entropy lowers the free energy. And so what you can see here, there's this temperature in formula. So if you increase the temperature, the entropy term becomes more and more important for determining your free energy. So if you go to very, very low temperatures, you basically want to minimize your enthalpy because the entropy is not very important. If you go to very high temperatures, then this becomes the dominant term. So a small intermezzo for, any questions so far? Yes.
Should you also take into account the energy and entropy of the surrounding?
Yes.
So the water cage when the hydrophobic residues are
Yes.
outside?
Those are also important, yes. Anyone else? Alright. So then a small intermezzo, so the entropy and energy and enthalpy what we have talked about so far are properties of macrostate. So that's, for example, the folded state or the unfolded state. So for example, this whole ensemble would be a macrostate, so this is the folded protein. And then these macrostates consist of an ensemble of microstates. So these are all the individual configurations that are in this macrostate. So if you talk about a microstate, you're really talking about one specific structure. If you talk about the macrostate, you're talking about more broader terms like the folded or the unfolded state. So what we can do to calculate the properties of a macrostate is that we take a weighted average of the all the microstates in that ensemble, and we call this the ensemble average. So what we do is, for example, you have it can be any property. Take for example the enthalpy. So what you would do to calculate the enthalpy of a folded state is to multiply the enthalpy of each individual configuration with its probability, and you divide it by the sum of all probabilities. And quite often this is normalized so that the sum of these probabilities is 1. So then that cancels out. So if we apply this to our free energy, so we have our free energy of a state is the enthalpy minus temperature times the entropy. And then the enthalpy will be the weighted sum of these enthalpies. For the entropy, it's a bit more complicated term if we do this. And so we have our a Boltzmann factor times the sum of the probabilities times the log of these probabilities. And this will actually give us this very long formula to calculate the free energy. And so now we're going to do a small exercise. So we have this formula, which is quite long, but we can calculate these probabilities if we know all states in the system. So we have a probability is this a Boltzmann? This follows a Boltzmann distribution. So we have the exponent of our energy divided by this Boltzmann factor, and here we sum over all the take this factor of all the configurations in our system. So then we can fill in. So to simplify this, so we have a few constants. So we assume that we keep constant temperature. So we have our Boltzmann factor times the temperature, and we call this beta. And then we have our Boltzmann factor, which is the sum of all these individual Boltzmann weights in our system, and that's also a constant. That's also the same for all states in our system in this case. So now what you're going to do is fill this in the formula, and then simplify this formula. So see what cancels out what you are left with. For about 10 minutes. I'll give you a small hint halfway through. Oh yeah, yeah.
Zou je zetten niet uit? Logisch. Oh, eerst
Je kan hem in theorie nog eerst uitzoeken.
Ja.
Kun je niet de som van de E-macht min 1 met het filterzet uitgaan? Want hier heb je som. Hier heb je som. Je theorie zet met.
Alright, just a small hint to help you out. The final, if you're, so your final result should be something, should be a log of something. If you get there, then you know you're done.
Dit weer.
Zeker dat je nog alleen met mij werkt. Kunnen we nu dit
Hier heb je sowieso al een lijn in elkaar. Volgens mij beta min
Niet zo goed. Gaan we dat zo doen?
Ja, maar dan kunnen we ook bij
Een beetje.
heel veel een breuk tot een wacht. Maar ik wel de
Ja,
Alright, let's go through it together. So did anyone get to the final answer? What do you think, Dave? No? You saw a hand there? Do you think you know what the answer is? Shout. If you think you got it, shout. See if you...
The summation of minus e to the minus big E I theta divided by beta z times LZ.
Almost. It's somewhere on the way to the right answer, and it's not the final answer yet. But, it's a bit... Alright, so the first step, what we do is we fill this into our formula. Over C. Alright, so the next thing, what we can do, we have a log of a fraction. So we can write this as log of e to the minus beta ei minus the log of z. Times. Right, so the next thing, if we have log of an exponent, we can just take that out. So what we get, keep this. Alright. Everybody still with me?
Please yell if you're not.
Yes.
Where did the 1 divided by beta come from? In the
This one?
beginning? Yeah.
So we have them here, and because we take, so we have the sum of this whole thing.
Yeah, but where did it come from in the first one? Because it was k times t.
So this equals kbt in the original formula.
There's a lot of
I don't know how long it takes to come back, but anyone else?
I have a question. Is the second or the middle term in the bottom?
This one?
No, that one, yeah. Where did the beta come from the exponent?
That one was already there.
No, because you cancel out the ln in the previous step from the exponent, and then you remove the brackets, right?
Oh
There's
yes,
a beta in
you're
the
right.
exponent. Doesn't that one cancel out with the other beta?
Yes, exactly. That's why I forgot it.
Okay.
So you're
Yeah.
the first beta. So this one, that's this one.
Yes.
So we have beta equals 1 over kbt.
Oh yeah. Yes.
So that's kbt is 1 over beta. So
Yeah, I
that's
see.
where this one comes from. I'll just leave the screen on actually because it takes quite a while for it to get back. So everybody's with me now until this step. So actually, indeed, what we see is that this beta cancels out with this one.
Can you?
Go up. Yeah, so here, this beta cancels out with the beta here. And then I'll have to go back down. So here we have our sum. Minus, because we had this minus beta here. Hey, no, that's convenient. Because those are the same, so they will cancel out. So these two cancel out. So we're left with this. I'll take all the constants, so z is a constant, so I'll take them out of the sum. So we have minus 1 over beta z times ln z times the sum into the minus beta ei. So who can tell me what this is? This sum. It's on the screen. Yes. So our final answer. Is that one? Any questions about this one? The derivation is also in the book, so you can also have a look at it there. Alright, so what we then see is that, so this is our final answer. Oh, so our free energy is minus kb ln z. What that means is that it's proportional to the probability of finding a protein in that state. And then we can calculate the free energy difference if we just know the probabilities of the two states. So we have the log of our probability of our state 1 divided by our probability of our second state. Now you're probably wondering why on earth did we go through all this? If you think about simulations, if you do sampling, for example, to calculate this individual probability, we would have to know all the we have to sample all the configurations that are possible for a certain state, and that's actually not possible. Well, as where we go through this, if we look at these probabilities, so of the probability of being in one state or the other, these are things that we can actually sample quite easily. So, if we look at a simulation at different temperatures, so here we see our time in the simulation and our RMSD from native. So we have the native structure, and you calculate the distance, the average distance between the atoms in your structure. So if you have a low temperature, so this is 20 degrees, then you see that the protein has a very low RMSD all the time, so it's very close to its native state most of the time. If you go to higher and higher temperatures, you see that there's the RMSD becomes higher, so this peptide is actually unfolded for a certain fraction of time. And so what we can here see is that the fraction of time that it's folded. So here we have our probability of being in the folded state, and then 1 minus this probability is our probability to be in the unfolded state. Yes. So if we have our free energy landscape at our folded at room temperature, we see that the protein is most of the time in its folded state, and then here and a small fraction of time in the unfolded state. Now, what will this free energy landscape look like if we take, for example, the highest temperature? Yes, I see hands doing the right thing. So they go the other way around. So actually what you see here, so for this highest temperature, it's only about 22-23% of the time in its natively folded state. So our free energy landscape looks quite different for the same peptide. And this is also, so actually what you see here at low temperature, so the energy, the favorable interactions, you see here the folded structure. They dominate, but if you go to higher temperatures, then your entropy, so your this configuration of freedom, which has more in the unfolded state, becomes the dominant term. So this is also the explanation for general heat denaturation of proteins. So if we look at the free energy landscape, so far we've mainly looked at a certain reaction coordinate versus the free energy, and then you have a state with a energy with a transition barrier, and then your second state. This is, so depending on your conditions, this is actually not just a simple two-state process. So we have our multidimensional, like the maximum we can draw is 3, but it's much higher dimensional than that. And depending on the conditions that we take, and what reaction coordinate we choose, you only take like a section of this free energy landscape that we measure on. So if we go back to our simple peptide on the lattice. So these are all the possible states, only now they're connected. So for each step, there's one of these angles that bends with an angle of 90 degrees. And then these are all the possible transitions that the protein can make. And so to go from, for example, the fully extended state to here, the natively folded state, there's not just one way you can go, but you can go via any of these paths. So here I highlighted 3 of them, so you can go directly via one transition to the state, but you can also go via many other configurations, and you could even like zigzag through this entire thing, but then the whole picture becomes red, so that's not very useful. But you can go through any of these paths to get to the folded state, so it's not just like unfolded state, transition state, folded state. So some of the key concepts of this part of the lecture, so we have a free energy that depends on the entropy and the entropy of your system. We know that this free energy is proportional to the probability of finding the protein in a certain state, which means that if we want to calculate the free energy of going from one state to the other, so state A to state B, we can calculate this by taking the log of the probability of being in state B divided by the probability of state A. And the second one is, so we have these macro states, so these are these state A, state B, and they consist of a collection of a single conformations, which are the microstates of your system, and over which we can calculate these ensemble averages to calculate general properties of our state, like the entropy. So that's the first part of the lecture. Are there any questions? A lot of information. Then I think it's time for a break.